Okay, well, it's 6 o'clock, so that means that it's time for us to start. Hopefully the others will join soon. It really is nervous and a little bit excited. Yes, I'm sure. I'm sure you must be. Can you see that? I don't blame you for being nervous. Right, but you guys have to manage your nerves during your exam. Okay, you have to breathe deeply and talk to yourselves and tell yourselves not to get upset. Because you can't do maths if you are feeling emotional or upset about things. You need to have a strategy and say to yourself, you know, if I see something that I don't know how to do, I'm not going to let it throw me and upset me. I'm going to leave it. I'm going to move on. I'm going to do all the questions that I know how to do first, and then I'm going to worry about the things that I couldn't do, and I'll come back to them. So I believe what you guys are not allowed to do is you're not allowed to use highlighters in your answer books, but apparently you are allowed to use highlighters on the question paper. So that's good news. At least we can still use our highlighters for for paper 2. So yeah, go and highlight the things that you've left off and come back to them. Because of course you're going to take your question paper away with you. Yeah, absolutely. Can you see that? I can understand. Afrikaans tomorrow is going to be confusing. How did English go? My children also struggled with Afrikaans. They like just literally scraped through. How did English go, guys? Because you've written paper 1 for English. How was that? Not too bad. Yeah, it looked like a nice paper. Oh, that's good, Kashandra.
Yeah.
That's good. All right, well, that's wonderful. At least we're off to a good start. Okay, let's hope it stays that way. All right, let's get into our maths lesson. This is obviously the very last opportunity we have to talk about paper 1. So yeah, let's get into it. I thought what we could do this evening was look at probability and some fundamental counting principle. So what I've tried to do is I've tried to choose questions that are a little bit more difficult. These are things that I know the boys at school have asked me about. So yeah, that's why I just wanted to try and do the things that were a little bit more difficult with you guys. Let's get started. Oh, shame, Kanyisile, but it was actually okay. That's good. That's good. I'm glad to hear that it was all right. Okay, so this particular question here was, or is, a survey was conducted among 100 boys and 60 girls to determine how many of them watched TV in the period during which examinations were written. Their responses are shown in the partially completed table below. So we call this a two-way table or a contingency table because it basically looks at 2 things. So it's considering gender, male and female, with did watch TV or did not watch TV. Okay, so the first thing that they've asked us to do is calculate the values of A and B. So they like to do this. They like to leave gaps in the table, and then we have to come along and work out what those numbers are. All right, so what do you think? How are we going to work out the value of A? What do you think? Because remember, A plus 12 gives us 32. There we go. Quite right. Yes, can you see there? What do you want to ask?
Ma'am, I want to answer the question.
Go for it.
So, ma'am, first we'll have to find out the total of female who watch TV during examinations and who don't watch TV, and then subtract the amount we get for that with 160, and then we get the total for males, and then we subtract 80, and then we get A.
Absolutely. Okay, so here what we would have ended up with is we would have ended up with A being equal to 20 and B would have ended up being equal to 128. Okay, so here we've got 20, here we've got 28, and there's nothing to stop you from filling in these totals here as well. So this one would have been 100, and this one would have been 60. As they told us in the beginning, there were 100 boys and 60 girls. Okay, so we filled in our table. All right, in 11.2, they've said to us, are the events being male and did not watch TV during examinations mutually exclusive? Give a reason for your answer. So are the events being male and did not watch TV during examinations, are they mutually exclusive? Now, in order to be able to answer this question, of course, we need to know what mutually exclusive events are. So if I wasn't a maths teacher and I said to one of you, you need to explain these words to me, I don't understand what it means, what would you tell me? How would you explain to me that events are mutually exclusive? What would you say? Okay, absolutely. All right. So yes, they don't need each other to happen. That is true. But when they do happen, they exclude each other from happening. Okay, so there is no intersection between the two events. Not independent, not independent. Independent means something else. All right, so we need to be very, very clear. Let me just go down here. All right, so when things are mutually exclusive, it means they cannot happen at the same time. So mutually exclusive events cannot happen simultaneously. So think about it. An example of this would be you are in grade 12. So being in grade 12 and being in grade 11 are mutually exclusive events. If you're in grade 11, you can't be in grade 12. And if you're in grade 12, you can't be in grade 11. Okay, so mutually exclusive events means things that cannot happen at the same time. All right, so for example, if we put our hand into a pack of cards and we can either get a red card or we can get a black card, we can't get a card that is red and black. All right, so it would be mutually, those two, getting a red card or getting a black card would be mutually exclusive events. They cannot happen at the same time. All right, so in other words, the probability of A and B happening is always going to be equal to 0 for mutually exclusive events. All right. When we talk about events being independent, Tisha, that's something entirely different. Okay, so if we talk about independent events, okay, it means that the outcomes or the probabilities of the one event are not affected by the outcomes or the probabilities of another event. So the best way for me to explain this to you, all right, would be, let's think about this. Okay, so when your mom had you, your mom had a girl. Okay, so Kanyisile and the other girls that are here with us this evening, or Tisha, whatever. Okay, your mom had a girl. Then if your mom fell pregnant again and she had another baby, the fact that you're a girl has got nothing to do with the gender of the baby that your mom's now going to have. Okay, they're completely independent events. Another way to describe independent events is something like this. Like, let's say Neliswa and I were going to share a packet of sweets. Okay, or maybe not a packet of sweets because you take a sweet out and you'd eat it. Let's say I've got marbles. So I've got 3 red marbles and I've got 2 green marbles. Okay, so if I say to Neliswa, put your hand in the bag and take out a marble. When Neliswa does this, all right, she can either take out a red marble or she can take out a green marble. There are 5 marbles in the bag, so she has a 3 in 5 chance of choosing red and a 2 in 5 chance of choosing green. If Neliswa takes the marble out and she looks at it and she puts the marble back into the bag, and I say to her, okay, now choose another marble, these 2 events are going to be independent, okay, because there are still 3 marbles in the bag, okay, and there are still 3 red marbles in the bag. There are still 5 marbles in total, okay. But if I said to her, okay, Neliswa, I want you to take a marble, look at the color, and then I want you to put it on the side. You're not putting the marble back into the bag. What is going to happen to these probabilities over here? Well, 2 things. First of all, if she took a red marble out, it means there are only 2 red marbles left. Also, there are now 4 marbles in the bag. There are no longer 5 marbles. This is an example of dependent events. Okay, so in other words, the fact that we did not replace something changes the probabilities that the next event. Does that make sense to you? Okay, so when they ask us to prove that events are independent, which is where this is going, what they want us to show, and you have to learn this because this formula is not on your sheet, right, is that the probability of A and B is the same as the probability of A times the probability of B. We have to prove that. Okay, that the left-hand side equals the right-hand side. So if they say to us, are these events independent? We can't write down P of A and B equals P of A times P of B because we don't know if they're independent or not. If that's true, then they will be independent, but they could also not be. It could also not be true. All right, so what we have to do is we have to treat this like a trig identity where we work with the left-hand side and the right-hand side separately from one another. Okay, which is eventually was what's going to happen with this particular question. All right, so are the events mutually exclusive? The answer to this is no. They are not mutually exclusive because the probability of being male and not watching TV during the examinations is 20 out of 160. It's not equal to 0. Does that make sense to everybody? So the probability of being male and watching TV, there were 20 men, 20 boys, okay, that did not watch TV during the examinations. So because it's equal to 20 out of 160, it's not equal to 0. Okay, so therefore they are not mutually exclusive. So we wouldn't use any other words. We would say not mutually exclusive. Does that make sense to everybody? You can just give us an emoji. Does that make sense, guys? Cool. Lovely. Okay, good stuff. So let's go on to the next question. Question 11.3. Here it says to us, if a learner who participated in the survey is chosen at random, what is the probability that the learner, now very important, okay, they're asking us a question about probability. So our answer has to be given as a fraction. You can either write it as a fraction or as a decimal or as a percentage, it doesn't matter, okay, but just write, I mean, I always just write them as fractions. It really doesn't matter, any of them. But when they ask you for probability, they're not asking you for the number of learners. All right, they're asking you for the probability. Okay, so it has to be the number of whatever we are looking for out of the number of the total, or the total number of people that took part in the survey, which in this case would be 160. Okay, so a learner that participated in the survey that watched TV when the exams were written. So what would we say? How many students watched TV when the exams were written? What column are we looking at? Exactly. Okay, so 128, lovely. Okay, so the total number of people that watched TV during the exams was 128. Okay, so here, this total here. Okay, so here our probability watching TV is going to be 128 out of 160. Okay, and then we should remember to simplify our fractions. Is that 4 out of 5? Tisha, is this 4 out of 5? Yes, okay, all right, perfect. Now they're asking us for the probability, okay, that someone is not male and did not watch TV during the period. Okay, so is not male means what? If you're not male, you have to be? You have to be female, absolutely. Okay, so again, mutually exclusive. If you're male, well, I suppose with gender fluidity these days, we can't really say that, but traditionally speaking, all right, if we're male, we're not female, and if we're female, we're not male. Correct. So is not male means female, and did not watch TV means did watch TV. So what is the probability that somebody is female and watched TV? So Tisha, did you get that from saying 48 out of 160? 3 out of 40? Okay, so it would be this value over here out of the total. Okay. So here, not male. And did not watch TV would be 48 out of 160. You said 12. What did I do? Oh, sorry. I'm being stupid. Sorry. I beg your pardon. It says did not watch TV. So it's not that one. It's this one, isn't it? Okay. Sorry, guys. And did not watch TV. Beg your pardon. Should have looked carefully at what column we were working at. All right. So not male means female, did not watch TV. There were 12 females that did not watch TV during the exams. Okay, so there is a 12 in 160 possibility that someone was not male and did not watch TV. Okay, good stuff. Well done. All right, so that would have given us, because 12 out of 32, what we're doing now, all right, is that we are comparing. The 32 is not the total number of people that took part in the survey. The 32 is the number of people that did not watch TV, during the exams. Okay, so here what you're doing is that if you put it out of 32, you're not working with the information like it's a two-way table. All right, so we've got to consider the people that watched TV and also did not watch TV. All right, it's not out of 32, because 32 is only the people that did not watch TV. So this is a conditional probability, and conditional probability is not part of your, I mean, you can have something like that, it is possible, but it's not part of our syllabus. Okay, so they mean out of everybody. Okay, no problem. Okay, well, that really wasn't too bad. Let's go on and have a look at some other questions. All right, so here they have given us A and B are independent events. Okay. So the probability of A is 0,4. The probability of B is 0,25. They want us to represent the given information on a Venn diagram and indicate on the Venn diagram the probabilities associated with each region. All right, so how should I draw my Venn diagram? If A and B are independent, what does it mean? It means that the probability of A and B is equal to the probability of A times the probability of B. So I can calculate the value of the probability of A and B by multiplying 0,4 with 0,25. Okay, what does that give me? I have my calculator. 0,1. There we go. Gives me 0,1. So that area of intersection has a value of 0,1. So in other words now, I'm going to draw my Venn diagrams. I'm going to draw my circles first. They intersect with each other. There's A, there's B. Now I'm going to draw a box around them. Why does it have to do this? There we go. So in this area of intersection, okay, so here's the area of intersection. It's this bit over here in the center. That has a value of 0,1. That's what I've just calculated. Okay, so this has a value of 0,1. So what am I going to write here where I've just put the red dot? Am I going to write 0,4? No, quite right, can you see it? What am I going to write? There we go. That's it. No, perfect, 100%. Okay, so to get A only, I'm going to say 0,4 minus 0,1. So here I'm going to write 0,3. That's A only. Good. And to get B only, I'm going to do the same thing. I'm going to take 0,25 and I'm going to minus 0,1 and I'm going to be left with 0,15 indeed. Okay. Now what do I need to do? I'm almost finished my Venn diagram. There's just one last little thing that I need to do. What is that? Okay, so remember with this, I'm working with probabilities, right? So everything has to add up to. Exactly, I've got to consider if there's anything inside my sample space. Okay, because remember, when I add A and B together, okay, I've got A or B, all right, it's got to add up to 1. And if it doesn't add up to 1, it means that there's something that is neither A nor B. All right, so I'm doing this. I'm saying 0,3 plus 0,1 plus 0,15. That's what I'm doing. Okay, so when I add those up, I'm going to end up with 0,55. That's not 1. So now it means that there is something in my sample space. And I can work that out by saying 1 minus 0,55, that's going to give me 0,45, isn't it? Okay, so I've got 0,45 out here. So let's just, before we move on, let's just talk about the regions inside the sample space. So where the 0,1 is, this bit that I'm now highlighting in yellow, okay, this bit in yellow, that is A and B, okay? So the yellow bit is A and B. So in other words, both at the same time. So in other words, we could say something like this: you are 18 and you are in matric, for example. Okay, you both at the same time. I am a teacher and I work for Watobe. I'm both at the same time. Okay, what do I mean when I say A or B? How is that different to A and B? How is A or B different to A and B? So how is A or B different to A and B? Teacher or doctor, you can't be both. Well, actually, Tisha, when we say A or B, that's exactly what we mean. We mean A or B or both. Okay, so A or B, how do you like this? Okay, so A and B was the yellow. A or B means everything inside A, including that which is A and B, so that's what or means. It means A or B or both. Okay, that's A or B. Okay, so that's why we say it is the union of the sets. Okay, so the union of the sets is what gives us 0.55. That's A or B. A and B is only 0,1. Not A and also not B is 0,45. Is everybody happy with that? Is that making sense? You understand the difference between the word and the word or. Very, very important in maths, the difference between the word and or. Are we all good? Yeah, it's difficult to understand, isn't it? It is. I know it is a difficult concept. Okay, so A or B means A or B or both. So either that which is inside A, or that which is inside both A and B, or that which is inside B. That's what A or B means. Okay, A and B means only the intersection of A and B. Okay, whereas A or B includes the intersection, but also includes A only and B only. Does that make sense to you? Right, so if we have a look at the next question, they've asked us to determine the probability of A or not B. We've got to read so carefully here. So the probability of A or not B. So if it's A or not B, then it means that it's going to be 1 minus your B only, because it's not allowed to be B. So if it's A, because they say or not B, so that means it's only that which is B only that we are excluding. Okay, because if you are A, you can still be A and B. It just says or not B. It does not say and not B. Okay, so what we could do here is a couple of things. Okay, that which is A or not B would be 0,3 plus 0,1 plus 0,45. Okay, that's how we could work that out. Or as an alternative, we could say 1 minus 0,15 and we would end up with the same answer. Okay, just check that on your calculators. I don't have my calculator with me. That means, okay, so what you've just put there, Tisha, A union B, that's all. Okay, so I'll let me just write. Okay, so probability A and B, the intersection sign is that one. Okay, so this means the same as the probability of A and B. And here, the probability of A or B is the union. Okay. Right, Tisha? Good stuff. Okay, so whether we worked it out by doing that or whether we worked it out by saying 1 minus 0,15, we would have ended up with the same answer. All right, so we should have ended up with 0,85 either way. Okay, so 0,85, either which way you chose to do it. All right, now let's move on and let's talk a little bit about the fundamental counting principle. We've been speaking about probability. We've spoken about mutually exclusive events. We've had a look at Venn diagrams. We've had a look at independent events. So this next question, 11.2, is about the fundamental counting principle. What they've asked us to consider here is that there is a organization that manufactures cars, and they can choose to make cars in the following ways. So there are 5 different styles of body. As far as the interior colors are concerned, you can choose from blue, gray, black, and red. And as far as the exterior color of the car is concerned, you can choose from 6 colors. So either silver, blue, white, green, red, or gold. Now, what these people want to do is they want to put on a display of each possible variation of the car, but they do not want the interior color of the car to be the same as the exterior color. So if it's blue on the inside, it can't be blue on the outside as well. Or if it's black on the outside, okay, can't be black. Okay, the interior is black. There's red as well. So if it's red on the inside, it can't be red on the outside. Okay, so there are some things that we're going to need to exclude. So they want to display one of each possible variation of the car in their showroom. And they say that the showroom has a floor space of 500 square meters. And each car requires a floor space of 5 square meters. Is it going to be possible to display this? Justify your answer with necessary calculations. This is worth 6 marks. So this is one of those sort of the very last question in the paper. Right? Have any of you seen this question before? Can you see you've seen it? No. Okay. No. Really? Oh, that is so interesting. Okay, so some of us have and some of us haven't. Okay, absolutely, Kanisila. Okay, so let's work through this together, right? So let's clear a bit of space here, and then we can start doing this question. All right. So we need to consider that there are 5 body styles, 4 interior colors, and 6 exterior colors. All right. So I think the easiest way to do this particular question is to actually start in the middle with the interior colors. Okay. And say, okay, well, the interior color can be one of 4. There are 4 possible variations. So if we consider what happens when we talk about, so this is, yes, like it. So it can be blue, gray, black, or red. Okay. So let's consider, all right, if it's blue, right, there are 5 body styles that we could choose from. So we want to fill 3 boxes. Okay. If it's blue, on the inside, there are 5 particular different bodies that we could have. And over here on this side, there are 1, 2, 3, 4, 5 interiors that we are allowed to have. So 5 different body styles. If it's blue on the inside, it cannot be blue on the outside as well. So if our interior color is blue, then our exterior color cannot be blue. Does that make sense to everybody? Because they've told us here the interior color of the car must not be the same as the exterior color of the car. Everybody happy with that? Yes, it is Kanyisile, but remember the inside and the outside cannot be the same color. So that means we've got 1 less option. Okay, look here. The interior color of the car must not be the same as the exterior color. Okay, so even though there are 6 options, if it's blue on the inside, it cannot be blue on the outside. Okay, so that's why our exterior colors have reduced, our options have reduced by 1. Okay. All right, now let's consider. Now let's consider if it was gray. Okay, so again, there are 5 options for the outside of the vehicle. And if it's gray on the inside, oh, there are 6 options on the outside. Okay, because gray is not an interior color and an exterior color. Now let's consider if the car was black, right? Again, there would be 5 different bodies, 1 color on the inside, which is black, and 6 colors on the exterior, okay? Because I do not have an interior and an exterior that is black. And as far as red is concerned, if my interior is red, my exterior cannot be red. And I've got 5 different body styles that I can choose from. All right, so now what we want to do is we want to add these up. Well, first of all, we want to multiply. So here we would end up with 25. Here we would get 30. Here we would get 30. And here we would end up with 25. All right, so if we added those together, we would end up with 50 and 60, which would give us 110. So there would be 110 different possible combinations of car that we could make. Does that make sense to everybody? Are we all good, guys? All right. Now remember, each car takes 5 square meters. So in other words, what we would now need to do, if we wanted to use this display, we would take the 5 square meters multiplied by the 110 different cars that we would be able to show, would mean we would need 550 square meters of space. Is it possible for us to do this display? Because the showroom is only 500 square meters. No, it's not. Okay, so, oh, where on earth did we go? Sorry, guys, just give me 1 second. How? Sorry, I don't know what happened there. Okay, so 500 is smaller than 550, so therefore the display is not possible. Okay, does that make sense to everyone? Are we all good? Good. Yeah, it's probability, it's difficult. Okay, so we've just got one more question to do. That's this one. Got 15 minutes to go. All right, so again, this is a little bit more fundamental counting principle. I don't know if any of you have seen this question before. All right, so in 11.2, it tells us the letters of the word decimal are arranged to form a new word, also consisting of 7 letters. How many different arrangements are possible if letters may be repeated? If letters can be repeated, and we're trying to fill 7 blocks, we'd be able to fill 7 blocks in, well, the first block in 7 different ways, and the second block in 7 different ways, and the third block in 7 different ways. So if the letters can be repeated, this would be how much? 7 to the power of 7, whatever that enormous number is going to be. Does that make sense to everybody? So when I've got repetition, absolutely, that's when I can use exponential notation. All right, how much is that? 8235. Let's just move this out the way. So 823453. Oh, that's crazy, hey? Different arrangements that could be made. All right, now the letters may not be repeated. Ah, this is exactly it, Tisha. Exactly. This is one of the things that matric students struggle with the most, is when do we use factorial and when do we not use factorial? So factorial is when things cannot be repeated. Okay, so letters and numbers can be repeated, Tisha, but people cannot. So let's say that, you know, if there are 10 people wanting to sit in 10 chairs, only one person can sit in a chair. So once one person has sat down, there are now 9 people left to occupy 9 chairs. Okay, so that would be 10 factorial. Here, this would be 7 factorial. So if the letters cannot be repeated, then we would say 7 factorial. Okay, which means 7 times, not that you have to write this, you don't, you would just write what 7 factorial equals. But by 5, by 4, by 3, by 2, by 1. Because if we're not allowed to repeat, then once we've used a letter, our options have decreased by 1. Okay, and that's where the, I think it's 5040 comes from, if I'm not mistaken. Yes. Does that make sense, Tisha, as to when you would use exponential equation and when you would use exponential notation as opposed to factorial notation? Okay. All right, we're nearly there, guys. Now, the arrangements must start with a vowel and end in a consonant, and no repetition of letters is allowed. Okay, so how many vowels do we have in the word decimal? Count them. We have exactly. Okay, so in other words, we've got 3 different ways in which we can fill the first block. Okay, then we've got to fill the remaining 1, 2, 3, 4, 5, 6, 7 blocks. Okay, now as far as the word where it ends, it has to end in a consonant. So if there are 3 vowels, then there have to be 4 consonants, right? Good. That's it. Now, repetition of letters is not allowed. So if I've used a vowel in the first block and a consonant in the last block, that means that 2 letters have been used. So that's why I've got 5 by 4 by 3 by 2, 5 by 4 by 3 by 2 by 1. What am I missing here? 1, 2, 3, 4, 5, 6, 7, 8. Oh, because I've introduced an extra block. Okay, there we go. That makes sense. So I had 8 blocks instead of 7. Okay, so does that make sense to everybody? All right, if I've used one number here, sorry, 1 letter here and another letter here, there are 5 letters left. I've used 2, 1 vowel, 1 consonant. That leaves me with 5 letters. Okay, so because I'm not allowed to repeat them, there are 5 factorial ways in which they can be arranged. So this is 3 by 5 factorial by 4. Does that make sense to everybody? Good. 1440. Okay. So much sense. Lovely. Oh, I'm so glad. Awesome. Okay. All right. So now let's do the last question. Okay. So again, this is the very last question in the paper. It's supposed to be a particularly difficult question, etc., etc. Let's just work through it as quickly as we can because we've only got 10 minutes left. All right, so they've told us that there are T number of orange balls and 2 yellow balls in a bag. All right, Craig randomly selects one ball from the bag, records his choice, and returns the ball to the bag. He then randomly selects a second ball, records his choice, and returns it to the bag. It is known that the probability that Craig will select 2 balls of the same color from the bag is 52%. So that's either orange, orange, or yellow, yellow. Okay, so the best way for us to do this is to use a tree diagram. Okay, so remember, when Craig selects a ball, either it can be orange or it can be yellow. He records the color and he returns it to the bag. So either it's orange or it's yellow, or it's orange or it's yellow. We know that there are T orange balls. Okay, so there are T orange and there are 2 yellow. So that means the total number of balls in the bag is T plus 2. So that's going to be our denominator. T of them are orange, 2 of them are yellow. Remember, because he replaces the ball, okay, so here we've still got T over T plus 2. Here we would end up with 2 over T plus 2. Here we've got T over T plus 2. And here we've got 2 over T plus 2. Does that make sense to everybody? So orange, orange, and yellow, yellow. Okay. So remember, the probability of orange, orange plus the probability of yellow, yellow equals 0.52. So now orange, orange can be written as the product of those 2 probabilities. So that's going to give us T over T plus 2 times T over T plus 2. That is orange, orange. Yellow, yellow is going to be plus 2 over T plus 2 times 2 over T plus 2 equals 0.52. My battery on my laptop is like about to die. Okay, so now that we've made this equation, what we need to do is solve for T, the number of orange balls. Okay, so when we multiply fractions, we multiply our numerators. So that would give us T squared over multiply our denominators. That would give us T squared plus 4T plus 4. On this side, we'd end up with 4 over T squared plus 4T plus 4 equals 0.52. It was 0.52, wasn't it? Was it 52%? Yes, it was. Okay. So T squared plus 4T plus 4 is our denominator. So we're going to need to multiply our denominator by each, or going to multiply each fraction by our denominator. Okay, so that means that we're going to end up with T squared plus 4 is equal to, now 52, that would be what, 13 out of 25. And that would need to be multiplied by T squared plus 4T plus 4. Okay, so now what I want to do is cross multiply. So I'm going to put brackets around that and I'm going to cross multiply. So that's going to give me 25 times T squared plus 4 is equal to 13 times T squared plus 4T plus 4. Does that make sense to everybody? So we end up with 25T squared plus 100 is equal to 13T squared plus, that would be 52T plus 52. All right, so now let's get it into standard form. So this would leave us with 12t squared minus 52t plus 48 equals 0. And at this point over here, I haven't made any mistakes, hey, Nelly?
No.
No, okay, all right. At this stage here, I think what I would probably do is use the quadratic formula. You could divide through by, well, 12 doesn't go into 52, it does go into 48. You could certainly divide through by 2, but anyway, let's just use the quadratic formula. So t would be equal to 52 plus or minus negative 52 squared minus 4 times 12 times 48 all over 2 times 12. And we should be getting 2 answers for t. So either t is this or t is that. What are you guys getting as an answer? Okay, so either t is equal to 3 or t is equal to 4 over 3. Thank you, Isana. Okay, now, is it possible for t to be equal to 4 over 3? Can we have a fraction? Definitely not. Okay, lovely. We cannot have a fraction. Okay, because remember, t represents the number of orange balls. Okay, so there are 3 orange balls.